So in part 3, we're going to look at mid-ocean ridges. First, we're going to talk a little bit more about some of the other bits of evidence we have for understanding the mid-ocean ridges. This first diagram, what you're looking at, is one of the most important ones, especially for California. These are one of the best. So if you learn in plate tectonics, generally you have the subducting slab drags oceanic lithosphere down under some other piece of lithosphere. But if that piece of oceanic lithosphere happens to be dragged down under another piece of oceanic lithosphere and happens to have a piece of continent attached to it, or if that subducting slab detaches, either one of these processes can potentially bring ocean floor up to the surface, especially if you have some mound building and or erosion taking place. And so we call these pieces of sea floor that have sort of found their way onto the continents, we call them the Ophiolites. You've been on my mind since the flood. Ophiolites. We also have submarines that have visited mid-ocean ridges. We have autonomous underwater vehicles that have visited mid-ocean ridges. This is actually one of our best tools because it can get a little sketchy and hairy on some of those mid-ocean ridges. Just for example, this one's actually not visiting the mid-ocean ridge. This one is about to visit the most dangerous glacier in Antarctica. But I happen to know some of these people, so yeah, and this sub is awesome. So yeah. We also have drilled into mid-ocean ridges quite a bit and pulled up lots of samples. This is the Jody's Resolution. This is a drill rig that can go through the entire depth of the ocean and drill through several kilometers of ocean crust if everything is going well. Good times. We also have instrumentation mounted on the mid-ocean ridge. This is the cabled axial seamount array. This is a path of a cable. It takes you to a data processing center. We have a whole array of instrumentation literally mounted everywhere all over this mid-ocean ridge complex, looking at various features and processes taking place. This is an exciting time to study mid-ocean ridges. There's a lot of data coming online that we're only barely beginning to make sense of, so be ready to discover stuff. A little detail of this, we have like seismometers, we have cameras, we have things sampling fluids coming out of cracks in the ocean floor. We even have like DNA because like this is kind of like prehistoric life down here. We want to know what we might have evolved from and all that stuff. We also have things for temperature, conductivity. Oh my god, all this stuff. I mean, we have like just behold the wonder. And by the way, this is what your homework is going to be on, so yep. So we're going to now go into a little bit about the oceanic crust structure. So generally, our mid-ocean ridge volcanism brings lava to the seafloor. That water is going to be pretty darn cold, have an extremely high heat capacity, so it's going to quench the lava almost instantaneously. And you're going to get these things called pillow basalts. These are, so the lava basically solidifies instantaneously, turns almost to glass on the right where it makes contact with the water, but then the lava inside takes a little bit longer to cool and develops a slightly coarser texture. It's still aphonetic. And we call them pillows. For scale, this is an outcrop of pillow basalt, I think somewhere in Idaho. Exactly how you get pillow basalts in Idaho. But gives you a nice idea of the scale of these things relative to, we're going to assume these are typical people. But never take anything, be a little skeptical. At greater depth, the lava is still going to cool reasonably quickly, but it's not going to be in direct contact with the ocean water. It's going to be getting in contact with the sides of the rift. And so it's going to be cooler right up on the side of the rift than where the lava is being injected through the spreading ridge. And so you're going to get these large parallel sheets of basalt extending for some distance. We call them sheeted dikes. These will go down about a kilometer or so, maybe a little deeper. deeper. And then finally, at great depth, the magma takes a much longer time to cool and crystallize, and will slowly but surely crystallize into gabbros. Because when the crystals get wet, these are chemically identical to your sheeted dikes and pillow basalts, but they have crystals you can see mostly. Then finally, below that, you get your peridotite. So the center of the ridge is usually defined by an axial valley. Because you have because while the heat generally makes the crust lighter, because you don't have any lithosphere mantle right at the mission ridge, the lithosphere crust is going to be a little bit lighter and tend to float up on the mantle. However, right at the axial valley, this magma chamber is a little lower density than the surrounding mantle around it, so that new, freshly erupted crust is going to sort of sink a little bit relative to its surroundings. You're going to get a series of these normal fault scarps, biggest one which will define the axial valley. As you can see, by the way, here, this is definitely not to scale, but you have your pill basalts, your sheeted dikes, and your gabbros, and then finally your peridotite once you start getting into the mantle. And this is going to continue throughout here. It just takes a long time to draw this on a typical diagram, so we don't worry about it. Now, what you're also seeing is fluid going through the mid-ocean, through these cracks, through the spaces between the pillow basalts, down between the sheeted dikes, and then sort of generally stopping maybe around the gabbro, maybe getting through some of those cracks, down further. This ocean water will heat up as it gets closer to the magma chamber, picking up that's sort of usually present between the gabbro and the sheeted dikes. It will slowly but surely chemically weather, because hot water can dissolve a lot of minerals that cold water does not dissolve. And so you'll have this very hot mineral-laden water. You may wonder, wait, how do you get water to get this hot? Oh. One of the things that helps is you're under a lot of pressure. Water under pressure will stay liquid at much higher temperatures than water at Earth's surface. So this water will then sort of get heated, get a little less dense, come up in the axial valley at these vents, laden with nutrients. As it hits the cold water, however, it can no longer hold all those minerals. So all those minerals will start to precipitate out. You'll get radon, sulfide, hydrogen sulfide, iron sulfide. Who likes pyrite? Yeah, these hydrothermal vents on the seafloor are a great place to find a lot of it. In fact, and what you'll even see are these little sort of chimney structures where all these minerals just basically drop out as the water suddenly becomes too cold to hold all those minerals that were dissolved at greater depth. Further away, you'll still see this raining out of the more and more minerals. You'll see manganese. You'll see other exciting things rain out. And this is actually the basis for some of the world's first metal mines. Remember I told you about those Ophiolites? One of the most spectacular ones on the planet, seriously, and no offense, California, we love you, but one of the most spectacular Ophiolites is on the island of Cyprus, where a mid-ocean ridge literally got pushed up onto the land surface through some sort of interesting process as the Mediterranean basin closed. Even back in the times of the Greeks, people realized there were valuable metal deposits and could figure out technology to mine and refine these. And you might notice this distinctive green. Yeah, there's some of that peridotite and serpentinization you're looking at. This is pretty awesome stuff. Also, because you have all these sort of chemical reactions, wherever you have a chemical reaction releasing energy, especially one involving oxygen or sulfur, in the presence of water, you're probably having life. Sulfur and oxygen behave fairly similar to each other in a chemical fashion. Not that I recommend any one of us breathe sulfur, but there's plenty of organisms that can essentially use sulfur the way humans and other organisms at the surface might use oxygen. We call them chemosynthetics, and they form the basis for our food web in these communities. So back in 1960s, we thought the ocean floor was basically devoid of life. Then we started saying submarines to some of these mid-ocean ridges once we started realizing what they're like. And suddenly it's like, my God, they're teeming with life. Whoa! So as you get further away from the mid-ocean ridge, your crust is going to start to subside. This is all going to be about, it's not so much distance from your ridge, it's all about time. Over time, your lithosphere is going to get thicker as more of that mantle becomes solid and attaches itself to the crust in solid form, making it less buoyant. And as it cools, it's also going to get less buoyant. So slow spreading ridges tend to be, all spreading ridges tend to be about the same height, not exactly, not perfectly, but we'll just, but the fast spreading ridges tend to be a lot broader because you have a lot of young and therefore warmer material a lot further away from the ridge. Now, between the mid-ocean ridges, you often have these things called transform faults and fracture zones. So these are, one of these actually runs right through California, a transform fault between the Juan de Fuca Ridge and the East Pacific Rise, or at least a branch of it in the Gulf of California, if you consider the Gulf of California that. But these are sort of accommodating the fact that because Earth is a circle, any motion on it is a rotation. And so when you have a rotational motion, it's a lot easier you don't really get the scissors like spreading at mid-ocean ridges, you get spreading like this. Instead of one segment spreading a little faster, one segment spreading a little slower, this transform can accommodate difference in spreading rate between these. And so while people generally see two offset features like this, think, oh, this feature is moving this way, the reality is if you stand here, this would be a left lateral fault in this particular case. Now, beyond the transform faults, you have these fracture zones. In these two cases, there's usually not a major difference in velocity between the ocean crust here and the ocean crust here, at least horizontally. There might be fractions of a centimeter per year, just because this ridge might be going just a little bit faster or a little slower than this one. But the bigger thing you see here is that because this crust is cooling off, the young crust cools off quicker than older crust, there's often vertical motion along these fracture zones, and also, God, I hate this, appreciable differences in lithosphere thickness on either side of these fracture zones. And so you can get actually decent-sized earthquakes on these, even though you don't really see much motion. This diagram might sort of hang on to a little bit, see what it's like, and think about it for a bit. Pause it even. This sort of takes our segue into features of the sea floor, the open ocean. We'll continue in part 4 of this video in a short little moment.